In the next section of locational marginal pricing, we'll consider an example. So, the example has two buses, bus 1 and bus 2, joined by a single line. The line has 100 megawatts of capacity, and it has an impedance of 0 plus 0.001 square root of minus 1. In other words, the impedance is purely imaginary. Let's let rho equal 1 be the angle reference bus. So that means the angle at bus 1 is known to be 0. Angle 2, theta 2, is the unknown. Bus 2, sigma equals 2, is the slack or price reference bus. We've got generators at both bus 1 and bus 2, and there's 110 megawatts of demand at bus 2. Let's suppose the generator at bus 1 is a cheap generator. The offer is capacity of 200 megawatts, and it's offering that capacity at $25 per megawatt hour. At bus 2, we have a more expensive generator, closer to the demand, whose offer price is $35 a megawatt hour. The line admittance, as usual, is the reciprocal of the impedance, and that gives us minus 1,000 square root of minus 1. The bus admittance matrix is a matrix whose entries, diagonal entries, are the sum of the admittances connected to the corresponding buses. So both bus 1 and bus 2 has exactly the admittance Y12 connected to it. The off-diagonal entries are minus the admittances joining the corresponding buses. Joining bus 1 to bus 2 is an admittance of Y12, and so minus that admittance appears in the corresponding 1,2 and 2,1 entries of the admittance matrix. So there are the values explicitly, and I can think of those entries as B11 square root minus 1, B12 square root minus 1, B21 square root minus 1, and B22 square root of minus 1. If we evaluate the submatrix of the Jacobian that corresponds to real power and angles at the condition of flat start, in other words, dP by d theta minus rho, that has got two entries corresponding to injections at bus 1 and bus 2, and it's with respect to theta minus rho, or theta minus 1, which is theta 2, the unknown angle. So evaluating that gives us minus B12 and B12, which is minus 1,000 and 1,000 respectively. Consequently, the DC power flow constraints are J, that matrix, times theta minus rho is equal to the corresponding injections at bus 1, which is P1, and the net injection at bus 2, which is P2 minus D overline 2. If we plug in J and observe again that theta minus rho is theta 2, we get these power flow equality constraints. If we want to eliminate the angles, we can do that by first writing down power balance. Clearly the generations have to meet the demand, and then solving for theta 2 by taking the appropriate entry of J corresponding to minus sigma, taking the inverse of that 1 by 1 matrix and multiplying it by P1. So J minus sigma involves deleting the second row of J corresponding to the price reference or slack bus, and that means we delete sigma minus 2 to get J minus 2. That leaves us with the minus the 1 by 1 matrix whose entry is minus 1,000. The inverse of that is minus 0.001. So we can observe that theta 2 is equal to minus 0.001 times P1. And just to observe, the angle reference bus is bus rho equals 1, whereas the price reference bus is sigma equals 2. So this example is showing that these two buses can be different. We then finally write down the power flow equations explicitly. Power balance, and theta 2 is equal to minus 0.001 times P1. Notice that if P1 is positive, that is to say we're injecting power at bus 1, as we'd normally expect in a generator, that would produce theta 2 being a negative number times P1, which would result in theta 2 being less than 0, less than theta 1, and that is an example of the familiar observation of power engineers that power flows from higher to lower angles. Let's suppose that the real power flow limit of 100 megawatts applies only in the direction of the angle of the arrow in figure 9.1. Going back to figure 9.1, that's from bus 1 to bus 2. We'll ignore the corresponding constraint in the other direction. So if we ignore that constraint, then the line flow constraint specified by K, theta minus rho is less than or equal to D, where our constraint is determined by the flow in the 1-2 direction, and its capacity is 100 megawatts or 100 per unit megawatts. The matrix K is given by minus B12, which is minus 1,000. So our constraint is K times theta 2 is less than or equal to D, which, substituting, says that minus 1,000 theta 2 is less than or equal to 100, which means that theta 2 is greater than or equal to minus 0.1. So notice that if theta 2 is greater than minus 0.1, we could observe that the absolute value of theta 2 is less than 0.1, and in those cases, the sine of theta 1 minus theta 2, which is equal to the sine of minus theta 2, is pretty well approximated by the small angle approximation. That is to say, we've verified that for the conditions that are relevant to feasible line flows, the small angle approximation that justifies the DC power flow approximation is pretty reasonable. Our matrix of shift factors, actually it's a 1-by-1 matrix, is given by K times J minus sigma inverse, which is minus 1,000 times minus 0.001. Multiplying them together, we get the 1-by-1 matrix 1. What that tells us is that if P1 is injected at bus 1 and the same amount of power is withdrawn at bus 2, then how much power will flow on the line? Well, shift factor is 1 times the injected power at bus 1. That gives us 1 times P1, or P1. So that says that P1 amount of power will flow on the line between bus 1 and bus 2. On the other hand, if P2 is injected at bus 2, which is where generator 2 is, and withdrawn at bus 2, then no power will flow on the line between bus 1 and bus 2. Actually, that was pretty obvious from the picture. The system equality and inequality constraints with angles eliminated are therefore power balance and power flow constraints, where we observe that there's no demand at bus 1, so that entry is 0. Since D is 100 and we've evaluated the various matrices, we get minus P1 minus P2 is minus D2 overline, where D2 overline is 110 megawatts, and P1 is less than or equal to 100. By the way, again, we could have seen this from the picture. You might think about how the constraints would be written down if the slack were at bus 1 instead of bus 2. Well, let's now figure out offer-based optimal power flow. P1, generator 1, is the cheaper generator, so we want to take as much power from it as possible, but the transmission constraint limits us to only taking 100 megawatts. So that tells us that P1 star is 100 megawatts, assuming that we can produce a feasible solution from the other generator. Well, if I have 110 megawatts of demand, P2 star, to make up the 110, would need to be 10 megawatts. So indeed, P1 star is 100, P2 star is 10. The flow of on the line is exactly 100 megawatts, and indeed if we plugged in P1 star to J minus sigma inverse, that would give us that theta 2 star is minus 0.1. So that gives us the optimal angle, the angle at the optimal solution. Notice that both the generation at generator 1 and the generation at generator 2 are both between minimum and maximum limits. So the 4 generator constraints are not binding. None of the 4 generator constraints are binding. So by complementary slackness, the corresponding Lagrange multipliers all have to be 0. We could say that both generators are marginal. And in general, the number of marginal generators is at least one more than the number of binding transmission constraints. When we didn't have any transmission constraints, we had one marginal generator. With one binding constraint, we'll have two marginal generators, and so forth. First order optimality conditions are that for each K, generator 1, generator 2, we have that 0 is equal to that first line in the necessary conditions. The terms involving the Lagrange multipliers on the generator constraints are 0. CK is 0. The term corresponding to each generator is 0. AK is equal to -1 for generator K. So that tells us that 0 is equal to the offer or marginal cost, since we assume that the offers are equal to marginal costs, minus lambda K star. So for generator 1, that tells us that lambda 1 star is equal to $25 per megawatt hour, the offer at generator 1 from generator 1. At bus 2, this relation tells us that lambda 2 star is equal to the offer at generator 2, or $35 a megawatt hour. So the LMPs are $25 per megawatt hour and $35 per megawatt hour respectively. These are the costs per unit energy of delivering an additional infinitesimal amount of power to buses 1 and 2 respectively. To deliver some extra power to bus 1, we generate at bus 1, that would cost us 25. To deliver some extra power to bus 2, that would cost us 35. So that sets the LMP at bus 2. You might think about how the LMPs would change or wouldn't change if we change the choice of sigma or rho. If we now turn to the angles eliminated version of the formulation, we still have optimality conditions for both K equal 1 and 2 that have a similar flavor. We still have that the Lagrange multipliers on the generator constraints are 0, but now we have different terms for these AK hat and CK hat. Indeed, A is a single row and its entries consist of -1s, so AK is -1, meaning that the corresponding entry is minus lambda hat star. But now we've got, in multiplying the mu's, in fact there's only one entry in mu hat star, we've got the entries C hat K. They are the shift factors for the corresponding generators. For bus 2, the shift factor is 0. We obtain that $35 per megawatt hour, which is the marginal cost at bus 2, minus lambda hat star plus 0 times mu hat star is equal to 0. Rearranging, we obtain that $35 is equal to lambda hat star minus 0, so that tells us that $35 per megawatt hour is equal to lambda hat star. Indeed, that is the locational marginal price. Lambda hat star is the locational marginal price at the price reference or slack bus. Plugging in to the corresponding relationship for bus 1, again we have 0 is equal to marginal cost at bus 1, which is 25, minus lambda hat star, which we just evaluated to be 35, plus C hat K transpose U hat star. Again, C hat K is the shift factor. In this case, it's equal to 1 for injection at bus 1, and it's equal to -1 for injection it's equal to 1, and that means on rearranging these terms, we obtain that 25 is equal to lambda hat star minus 1 times mu hat star. Lambda hat star is 35, so mu hat star is the difference between them. Mu hat star is $10 per megawatt hour. Again, the LMP at the price reference bus sigma equal 2, is $35 per megawatt hour. The Lagrange multiplier on the transmission line constraint is $10 per megawatt hour. Well, let's try a larger example. We're going to go back to the previous 4-line, 4-bus example from section 3.8. It's got megawatt capacities and per unit impedances as shown. This is the same system as in section 3.8. We're going to assume that rho equals 0 is the angle reference bus. So the unknown angles are theta 1, theta 2, theta 3. The demand is 3,000 megawatts at bus 0, and bus sigma equals 0 is the price reference bus. So D over line 0 is 3,000 megawatts, and there's no demand elsewhere in this particular example. Let's assume that the transmission line capacities are respectively 3,000 megawatts, 3,000 megawatts, 300, and 3,000 in the directions implied by the arrows. So the constraints are in this direction from bus 1 to 0, from 2 to 1, 2 to 3, and 3 to 0. In general, there would be a similar constraint in the other direction, but we'll ignore those limits in the directions opposite to the arrows. The generation offers are, as we saw previously, $40, $20, and $50 per megawatt hour at buses 1, 2, and 3 respectively. The offered capacity at bus 1 is 1,500 megawatts, as is the offered capacity at bus 3. The offered capacity at bus 2 is only 1,000 megawatts. And as usual, we'll assume that the offers are set equal to marginal costs. So this is the same demand and offers as in the previous example, but now we have to satisfy the transmission constraints. We derived the DC power flow constraints for this problem. As usual, they're in the form J times theta minus rho is equal to P minus D over line. J we derived before. D over line, the vector of net injection, net demands, has value 0 at buses 1, 2, and 3, and it's only got a non-zero value at bus 0. The real power injections are from the generators are at buses 1, 2, and 3, and there's no injection at bus 0. So we can write this down in the form J times the unknown angles is equal to this vector of generations minus this vector of demands. Eliminating the angles yields power balance and angles written in terms of the net injections everywhere except at the slack bus, and that means generations at buses 1, 2, 3. The line flow constraints are in the form K times theta minus rho is less than or equal to D. The right-hand side of the constraint matrix is 3,000, 3,000, 300, and 3,000. And evaluating K, we met it before, is given by this matrix. So in general, in each row, there is either 2 entries corresponding to the from and to bus, or if the to bus or the from bus is the angle reference bus, there's only one non-zero entry in the corresponding row of K. The matrix of shift factors is K times J minus sigma inverse. Multiplying that together gives me these shift factors, and the augmented shift factor matrix, when I want to include net injections at the slack bus, is given by augmenting this matrix by a column of zeros. That column of zeros corresponds to the slack bus. The system equality and inequality constraints with angles eliminated are therefore power balance and shift factors times the injections except at the slack bus is less than or equal to the corresponding terms for the demands. That turns out to be 0 plus the demand limitations. Substituting in the known values, we get power balance and this constraint on generations at buses 1, 2, 3. Well, let's for a moment, although we've gone through and calculated the representation of the transmission constraints, let's ignore transmission constraints for a moment and consider offer-based economic dispatch ignoring transmission constraints. You may remember that the solution was P1 star is 1500, P2 star is 1000, P3 star is 500. If we plug those values in, we obtain flows of 1900, 400, 600, 1100, which are not less than or equal to the line limits. So that's not a feasible solution because it would produce a flow on the line from buses 2 to 3 of 600 megawatts when the limit was only 300 megawatts. Well, let's try something else. Let's start with the cheapest generation, which is generator 2. It offered 1,000 megawatts of capacity. If we tried that out, P2 equals 1,000, and for now let's assume P1 and P3 is 0, so we would only be able to meet 1,000 megawatts of demand. Then because the shift factor for injection at bus 2 onto the line from bus 2 to 3, the shift factor for that injection is 0.4. So if we inject 1,000 megawatts, the flow on the line between buses 2 and 3 would be 400 megawatts, which would still violate the constraint. You might ask yourself, will we actually be able to utilize all of the low price power from bus 2? Offer-based economic dispatch is sometimes explained by saying that the offer blocks, we can think of the generators making block offers, that the offer blocks are stacked up from lowest to highest offer price until the demand is met. If we use this analogy, we might be led to believe, since we'd first stack up the block from generator 1, we might be led to believe that we wouldn't be able to use all of the low-priced power from bus 2 in offer-based optimal power flow, since using that lowest-priced block alone would violate the transmission constraints because it would result in a flow of 500 megawatts. So let's think about that. Will we be able to utilize all of the low-priced power? Well, to find the offer-based optimal power flow solution, we need to use a formal optimization process. And using either the formulation of offer-based optimal power flow with angles represented or the formulation where we eliminated the angles, the problem is a linear program which can be solved, and it yields the following solution. P1 star is 750 megawatts, P2 star is 1,000, P3 star is 1,250. These are different from the unconstrained solution. And the resulting flow on the line from bus 2 to 3 is 300 megawatts. Moreover, generator 1 and generator 3 are both operating between their minimum and maximum capacity constraints. So only the generator constraint for generator 2 is binding. So for complementary slackness constraint, the Lagrange multipliers on all of the other generator constraints are 0. All of the lower bound generator inequality constraints are 0, and the upper bound constraint, lower bound Lagrange multipliers are 0 for all of the generators, and the upper bound Lagrange multiplier for generators 1 and 3 are 0. And again, we could say that generators 1 and 3 are marginal. Only the line constraint joining bus 2 to bus 3 is binding because the flows on the other lines are well below their capacities. So by complementary slackness, the Lagrange multipliers on all the other line constraints are 0. First order necessary conditions for our 4 generators. Let's use the angles included representation. Looks like this. The Lagrange multipliers for generators 1 and 3 are 0. Some of them for generator 2 are 0. CK in this formulation is 0. AK is minus 1. So again, that gives us that 0 is equal to the marginal cost minus lambda K star minus plus some terms involving the system constraints. For generators 1 and 3, these Lagrange multipliers are all 0, so those terms go away. So that means for generators 1 and 3, we've got the relationship. We saw a similar thing in the 2-bus example. The generator lambda k star is equal to the marginal cost. So for generator 1, lambda 1 star is $40 a megawatt hour. That's the LMP at bus 1. For generator 3, the Lagrange multiplier at bus 3 is $50 a megawatt hour. And these are, respectively, the cost per unit energy of delivering an additional infinitesimal amount of power to buses 1 and 3. We would deliver power to these buses by generating it locally. If we now consider the angles eliminated version, and the reason why I'm doing this is because it's convenient to extract some more of the Lagrange multipliers, what we can see in the angles eliminated version is that we have A hat k being equal to -1 for each generator, so that this term becomes minus lambda hat star. Again, as in the 2-bus case, we've got some shift factor related terms multiplying in to the vector of Lagrange multipliers on the system inequality constraints. Again, for generators 1 and 3, the upper and lower bound Lagrange multipliers are 0, and we can quote, we've already calculated these particular shift factors, and notice that the only non-zero term in this vector mu hat star is the term mu hat star 2, 3. So this will pull out the third term in the column of C hat k. So what we can do is observe that the LMPs at buses 1 and 3 also satisfy lambda 1 star is equal to $40 a megawatt hour, which is equal to the gradient, the marginal cost at generator 1, which is, by rearranging, equal to lambda hat star minus the shift factor 0.2 times mu hat star 2, 3. So 0.2 is the shift factor for bus 1, injection at bus 1 for flow on the line from 2 to 3. Similarly, for bus 3, we've got $50 a megawatt hour is equal to lambda hat star minus 0.2 times mu hat star 0.3. Again, and in this case, minus 0.2 is the shift factor for bus 3, for injection at bus 3. We've got two equations in two variables and two unknowns, namely lambda hat star and mu hat star 2, 3. So that enables us to solve for those unknowns. That gives us lambda hat star 2, 3 is $25 per megawatt hour. That's the Lagrange multiplier on the flow constraint. And lambda hat star is $45 a megawatt hour, which is the LMP at the price reference bus, which is bus 0. Therefore, the LMP at bus 0 is given by that price. So lambda star 0, that's the version from the angles included, is equal to the Lagrange multiplier on power balance in the angles eliminated. It's $45 per megawatt hour. Finally, we can calculate the LMP at bus 2. It's the LMP at the price reference bus minus the corresponding shift factor times mu hat star 2, 3, which gives us $35 per megawatt hour. That relationship is, of course, satisfied by analogous relationship is satisfied by all of the Lagrange multipliers on the previous, all of the LMPs on the previous pages. We use that to figure out mu hat star 2, 3. So substituting, we get flows that are, as shown, which are within our constraints. And putting that all together, we get generator 1 produces 750 megawatts. Its LMP is set by its offer price of $40 a megawatt hour. It's a marginal generator. Generator 2 produces 1,000 megawatts. Its LMP is $35 per megawatt hour, which is higher than its offer price at $20 per megawatt hour, but it's at full output. Generator 3 is at 1,250 megawatts. Its LMP is $50 per megawatt hour, which was set by its offer, and it's also marginal. The line from bus 2 to 3 is at its limit. The other lines are well below their limits, and the injection of 750, 1,000, and 1,250 provides for 3,000 megawatts of demand at bus 0. The LMP at bus 0 is $45 per megawatt hour. So let's look at some properties of LMPs that arise from my example. First, I'll observe that the LMPs can be different at every bus. There are 4 different LMPs in this 4-bus system. The LMPs can be the same or lower than the offer price at a bus. They're lower than the offer price if cheaper imports are feasible. They're same as the offer price if the generator is marginal. The LMPs can be higher than the offer price. Well, that I need to qualify that. I mean if no more capacity is available at the bus. The LMPs can be higher or lower at the demand bus compared to a generator bus. The LMP at the demand is higher than the LMPs at buses 1 and 2, and this is a typical case. But it's also possible for the LMP at the demand bus to be lower than the LMP at a generator bus. For example, it's lower than the LMP of $50 a megawatt at bus 3. Notice that the demand LMP of $45 per megawatt hour is lower than the generator LMP of $50 a megawatt hour. Power can flow from a bus with a higher LMP to a lower LMP. There's power flowing from bus 3, whose LMP is $50 a megawatt hour, to bus 0, whose LMP is only 45. Why would we allow that to happen? Well, injection at bus 3, it causes counterflow on the line from bus 3 to bus 2. That allows for all of the cheap generation at bus 2 to be utilized. The flow from bus 3 to bus 0 is actually a side effect of the generator injecting at bus 3. If we could change the shift factors, we'd change them in such a way as to decrease the flow from bus 3 to bus 0 and correspondingly produce more counterflow on the line from bus 3 to bus 2. Another property is that the LMPs can be higher than any generator offer price. That occurs if increasing demand necessitates decreasing generation at a cheap generator and then more than compensating at expensive generators. Similarly, or analogously, the LMPs can be lower than any generator offer price. And that occurs if increasing the demand by a megawatt, for example, allows for more than 1 megawatt increase at a cheap generator. LMPs can be lower than the transmission unconstrained price. The original offer-based economic dispatch solution ignoring transmission constraints had an unconstrained price of 50, but under offer-based optimal power flow, the LMP was $45 per megawatt hour at bus 0 at the demand bus. So let me emphasize that the transmission unconstrained price is definitely not equal to $45 per megawatt hour, which is the LMP at the demand. The LMPs can be higher than the transmission unconstrained price, and that occurred in the example in 9.5, where the solution ignoring transmission constraints, you can check it out, would result in an LMP of $25 per megawatt hour. I want to now turn to some other specific topics. First one is congestion rent and congestion cost. First, congestion rent. In the four-line, four-bus example, the demand would pay d over line 0 times its Lagrange multiplier, or LMP, lambda star naught. That would be 3,000 megawatts times $45 per megawatt hour, or $135,000 per hour. The generator at bus 1 is paid P1 star times lambda 1 star, which is 750 megawatts times $40 per megawatt hour, or $30,000 per hour. Similarly, generators 2 and 3 are paid $35,062. If we add up the total payment to the generators, that's $127,500, which is less than the payment by the demand. The difference between the payment by the demand minus the payment to the generators is called the congestion rent, sometimes called the merchandising surplus. and the congestion rent is $7,500 per hour in this example. The congestion rent is a revenue stream that accrues to the ISO. There are dollars coming in, dollars coming out. The dollars coming in is more than the dollars going out. Actually, we need to prove that, which we'll do in a few moments. It's a revenue stream that accrues to the ISO. It is disbursed back to market participants through so-called financial transmission rights, which in ERCOT are known as congestion revenue rights. We'll see that in Chapter 11. And as I mentioned, the congestion rent is sometimes called the merchandising surplus. Another related but different concept is the congestion cost, most properly the revealed congestion cost, because it's what the offers reflect. We're always assuming that the offers in fact reveal the true marginal costs, but precisely speaking we should call it the revealed congestion cost. It's defined as the difference between the cost of dispatch under offer-based optimal power flow minus the cost of dispatch ignoring transmission constraints. Congestion cost represents the increased cost of fuel needed due to the finite capability of the transmission network. In this case, the congestion cost is $7,500, which happens to be the same as the congestion rent. However, that's an artifact of this rather extreme example. The congestion rent is not generally equal to the congestion cost. They happen to be equal in this example, but more typically the congestion rent is much larger than the congestion cost. They're often confused, and sometimes people use the phrase congestion cost for what I've called congestion rent, so it's worth clarifying the definition. Although they're either both zero or both non-zero, there's actually no direct relationship between them. So one cannot judge from the congestion rent what the value of congestion cost will be. Congestion rent, however, is either zero or non-negative. That's true also of congestion cost. It's pretty obvious for congestion cost because it's the increased cost of fuel. For the congestion rent, however, that needs a little bit of proof. So let's prove it, that congestion rent is always non-negative. So by definition, the congestion rent is the payment by demand minus the payment to the generators, which is the vector of Lagrange multipliers, vector of locational marginal prices, which are Lagrange multipliers on the power balance at the buses, multiplied into the corresponding net demands. This multiplying into the demands yields the payment by demand. Subtracting from that, multiplying it into the real powers, gives the payment to the generators. So from section 9.4, we have that for some choices of Lagrange multipliers in the angles eliminated formulation, that the Lmps are equal to the Lmp at the price reference bus minus appropriate terms involving the shift factors times the Lagrange multipliers on the inequality constraints. The column of C hat corresponding to the price reference bus is equal to the zero vector. So if we collect these expressions together into a single vector equation, we get lambda star is equal to a vector of 1s multiplied into lambda hat star. That just creates a vector that's full of lambda hat stars minus the appropriate terms with the shift factors. So we can plug that into the congestion rent expression. The congestion rent expression is equal to lambda star hat d over line minus p star. We just proved that that's equal to 1 times lambda hat star minus c hat transpose mu hat star transposed into the net demand minus production. Let me transpose that whole expression. That pulls out lambda hat star transpose times 1 transpose d overline minus 1 transpose p star minus mu hat star transpose c hat d overline minus p star. By supply demand balance, 1 transpose d hat minus 1 transpose P star is 0, so that leaves me with the term involving the Lagrange multipliers and the constraints. Let's let C hat Lk be the row of C hat. Previously I've mostly referred to columns of C hat, but let C hat Lk in parenthesis be the row of C hat corresponding to the line joining L and K. And let P over line Lk be the corresponding line limit, and mu hat star Lk be the corresponding Lagrange multiplier on the corresponding line limit constraint, one of these constraints. Then my expression for congestion rent, on the previous page we showed it's equal to this in terms of the mu's. I can think of I can rearrange that to get rid of the minus sign by swapping the P star and the D. Then I can think of this as a summation over the constraints broken up into the constraints whose Lagrange multipliers are 0 plus the constraints whose Lagrange multipliers are non-zero. For the constraints whose Lagrange multipliers are 0, that is, these Lagrange multipliers are 0, so each of these terms in the sum is 0, so that gives me 0. For the terms where the Lagrange multiplier is non-zero, however, complementary slackness tells me that the corresponding constraint must be binding. In other words, C hat Lk, that row multiplied into the net demand for the binding constraints, must equal the limit. That gives me an expression for the congestion rent that's equal to the sum over the non-zero Lagrange multipliers of the product of non-zero value times P over line. So that's greater than or equal to 0. It could only be equal to 0 if, for example, there were no terms in this summation. So the payment by demand minus payment to the generators is greater than or equal to 0. We've also proved, in fact, as part of the proof, that the congestion rent is equal to the sum over the binding line constraints of the product of the corresponding Lagrange multiplier and the flow limit. In the flow gate, so-called flow gate transmission rights mechanism, we associate congestion rent individually to each binding constraint. In fact, the old ERCOT zonal market used a flow gate transmission rights mechanism based on the interzonal flow limits. Now we're going to consider one more final property. We're going to consider a related property that's useful that will be useful in the discussion of financial transmission rights. So far we've considered demands D overline and the corresponding generation P star in the offer-based optimal power flow. Let's now suppose that someone comes up with a different vector of demands, let me call it D primed, and a different vector of generations, P primed. Let's suppose that D primed and P primed satisfy the system constraints. In other words, they satisfy power balance and they satisfy that the line constraints are within the limits. We're going to consider the congestion rent under the following circumstances, which will turn out to be relevant to the case of financial transmission rights. We're going to assume that the prices, lambda star, were determined from the offer-based optimal power flow solution, corresponding demand D overline and generation P star. But we're going to assume that the demand and generation quantities are given by D primed and P primed, and we're going to consider the corresponding congestion rent for that demand and generation, but using the prices from offer-based economic dispatch. So, we get the following corollary. Let's suppose the Lmps were determined from offer-based economic power flow corresponding to demand D and generation P star. Let's suppose D primed and P primed are any vectors of demand and generation respectively that satisfy the system constraints. So we've got power balance and inequality constraints. They can differ. D prime could differ from D overline, P prime could differ from P star. But nevertheless, I claim that the congestion rent under d prime p prime using prices lambda star would be less than or equal to the congestion rent under d primed and p star, where lambda star is the price corresponding to that optimal dispatch p star. How do we prove it? Well, what's the congestion rent under d prime p prime? Similar expression to previously, we can write that down using the angles eliminated version of the Lagrange multipliers, of course multiplying into d prime minus p prime. We've got our, again taking the transpose, we've got our power balance story and the story with the Lagrange multipliers. Because of power balance, we drop out this first term, we're left with a term that's minus Lagrange multipliers times constraints. Again, swapping p and d, we get term Lagrange multipliers transpose times c hat times p prime minus d prime. Again, we're going to separate it into terms where the Lagrange multipliers are 0 and terms where the Lagrange multipliers are non-zero. Again, for the terms where the Lagrange multipliers are 0, that zeroes out that first summation. For the terms where the Lagrange multipliers are non-zero, we've got a sum over non-zero Lagrange multipliers of a term that's the corresponding row times p prime minus d prime. Now, since p prime d prime satisfied the system inequality constraints, that means the flow that would have resulted from p prime d prime had to be less than or equal to p over line lk. Since I'm multiplying that by a non-negative number, that means each term here is less than or equal to mu hat star lk times p over line lk. But that is in turn equal to lambda star transpose d prime minus p star. So we've just proved that the congestion rent under this modified demand is the same as the congestion rent under the original demand that gave rise to the prices lambda star.